Hello, everyone. We are working on a kernel for an operating system we are written from scratch. Last time, if you've been following along, you know that last time we've finished working on the first stage of the bootloader. And so what we did is we finished the first stage of the bootloader that basically loads the second stage. We've also written a small utility that basically burns the first stage onto the disk image that we have. We've left here a to-do, which basically means that we need to come back and write the sector, the start sector of the second stage onto that first stage so that it knows where to load it from. And we also automated the creation of we've automated the creation of the disk image that we are generating and putting the second stage on. For now, the second stage we have is just a test file that we've generated. We've written a few bytes in it so that it has the magic bytes we want. But today what we'll do is I believe we'll come back to this first stage so that we can do the thing that we've talked about before, which is relocating the code of this first stage higher up in the memory so that we can have more free memory to play with. We will also come back to the make boot utility and basically do this to do here that's missing. And I guess the last thing that we will do is we will start working on the second stage. All right, let's get to it. Okay, so let's start with the first stage. So what we want to do is we want this whole stage to be located at 0x600. Hold on, let me pull up a memory map. Here, I think I have something in the documentation. Yeah, looks good. So the memory layout for the lower 1 megabyte of memory looks something like this. The first 1 KB plus 256 bytes are used by the BIOS. And then the usable memory starts at 0x500 and it ends at 0x7FFFFF. Right, so let's take a look at what memory looks like on the first megabyte of the real mode address space. So we have here a bit more than a kilobyte. That's unusable, that's memory used by the BIOS. Then we have about 490 kilobytes of user memory that we are allowed to use. And then here we have the EBDA. That's also used by the BIOS. Here we have the memory display, the BIOS display. Here we have the BIOS video, and here we have expansions and the BIOS code that's at the end of the first megabyte. So here you can see that the only region that we can actually use is this region here between 0x500 and 0x7FFFFF, right? Except that we have our, the bootloader has loaded our first sector at 7C00. We have all these bytes here. We have about 30 kilobytes of memory that's wasted because we are starting execution at 7C00. So if we want to actually use this memory here, what we need to do is we want to move this code, that's this one sector, this 512 bytes that are loaded here by the BIOS. We want to move them somewhere in this region between 0x600 and 0x800. One sector is 512 bytes, which is 0x200 in hexadecimal. So that's why. Right, so first thing I want to do is I want to go all the way to the top of the file where we have the org directive. And I just want to change the org from 7C00 to 600 because once we are done with the relocation, we want the assembler to actually calculate the addresses as if we already are at 0x600, right? Okay, so once that is done, I just want to come over here, create a label, called relocate. And here what we want to do is we want to get the address of start. And then we want to know basically how long this is. And we know that this is 1 sector long. And then we want to copy each byte to its destination. If you know how calls work, so when you do something like call some function, what happens is that so that we know where to return, the call will push into the stack. So basically, call will be. Let me just put this as a comment. So the call will be a push of the return address, and then it jumps to well the address of the function, right? And then at the end of a function, you find the ret keyword, which basically does the opposite. It does the pop of the return address, and then it jumps to the ret address, right? So what we are going to do is, since here it will push the effective address, the address to which the current instruction pointer is pointing to the stack, then we will use this to tell us which address we are at this instruction here. Okay, so here we will call relocate. Of course. Right. So once we are here, we can pop relocate to register here. I'll put it in SI. But now what we have is that we know the address of this instruction, right? And what we want to know is the address of this instruction, the first one, the start label. So what we can do is that since these instructions do not change, then we can just sub SI with the difference between relocate, and start, right? So this would give us the length of all the instructions between these two labels. And then we just need to subtract that from this address here. The difference between the two will give us 7C00, which is the address that we are looking for. So this is a neat trick we can use here to avoid hard coding the address we get loaded in, so that if we want to run our bootloader on something other than x86, we'd still have that option without having to change the address basically in the code. So that's neat, right? Okay, so once we have that address here, so we know that this is the address of start. What we can do now is that we want to we want the address of the destination, right? So what we will do now is we will move to the destination index register. We'll move to x600, for example. Right. So that's that. And then what we want to do is start up by clearing the stack. So let's do that. Let's actually set into DI the address of 0x500. So the very first address that we want to, basically the end of our stack, right? So let's set that to DI, and then we'll move to, so actually what I want to do is I want to use this instruction here, store string word, to basically store the content of AX into DI, right? And then it will increment DI. So I want to loop on DI until it reaches well 0x100 or 256 bytes, and then I want to store the 0 byte that's on AX, because here, if we go back to the code again, you can see that AX is 0, so we know it's 0. Right. So, and we want to repeat this for, well, we want to do this for 256 bytes, but since we want to move words, that means that we need to divide by 2, so it'll be 128 iterations, right? Okay, so what we want to do is we want to store using this this instruction here, store string word. We can just write a loop, basically, that checks a counter that gets incremented every step, and when it reaches the correct value, then we stop the loop, right? But there is a better way to do it, which is to use this instruction here that was designed for exactly that purpose. And the way this works, if we go down to this operation algorithm here, if address size is 16, and we are in real mode, so this is the case we're in. So use CX for count register, implicit source destination operand for memory use SIDI. So okay, this we already knew about. Then what we are going to do is, while count register is not 0, interrupts, we don't care. We decrement the count register. If it hits 0, then exit the loop. Right, if the prefix is repeat NZ or repeat NE, and 0 flag is 1, then exit the while loop. Otherwise, we just execute the associated instruction here. So the way we are going to use that is, so I'll move to CX. So it'll be 128, which is so half of 256 is 128. That's the number of times we want to repeat this instruction, the move instruction, or the store instruction, sorry. And then here we'll do rip NZ, store string word, and we'll need to check that we have everything right. So here we are at DI, destination is 0x500, and we store 128 words, every word being 2 bytes. That means we store 256 bytes. The value comes from AX, which is 0, so we're doing fine, right? So here we are, we basically zeroed this stack between 0x500 and 0x600, right? Somewhere here, right? So now what we want to do is we want to start copying the code that we have between SI, which is this address we've calculated before, and DI, which will now be after this instruction. DI now contains 0x600, since if we go back to look at store string word, here we go. So AL df equals 0, then DI is incremented, right? So we are good to go. And here we can see that we've already cleared the direction flag, so it is equal to 0. So DI will actually get incremented. So good, great. So now what we want to do, DI is at the correct value, is at 0x600. We have the correct, I guess, source address in SI. So what we want to do is we want to use the same instruction. So we just need to move CX, and here we want to move a full sector, so 512 bytes. But what we're moving is actually words, so we need to divide that by 2. Sorry, so we move to 56, right? And here rep nz, and instead of store string word, we'll use move string word, which is basically the same thing, except that it takes the word from si and moves it to di, and then increments si and di. And the rep nz will decrement cx until it reaches 0. So that's it. So now what we have here is that we have copied all our code to the correct address. Now what we want to do is we want to actually jump to that address, because here the instruction pointer is still at 0x7c something, right? So what we want to do is we want to jump to the next instruction that we want to call, which is this one. And that instruction, since we have this org at 0x600, it will be correctly addressed at 0x600 plus the offset of this instruction here, right, relative to the start. So what we can do now is just jump. We just need to jump there, right? Let's just recompile everything and rerun box. All right. So yeah, shouldn't forget to put the breakpoint, continue, and now we start stepping through the code, push CS, pop DS, okay. And then here we have the call to, and you can see the address that we are calling is 7C13, which is the label for the relocation code. And what I want to do before we jump into that, I just want to run reg, which basically dumps the registers. You can see here that the IP instruction pointer is pointing to 7C10, which is the instruction for this call. AX is zeroed. And actually, I think if I do sreg, we'd get, yeah, sreg is good. So we have the code segment is at 0, the segment is at 0, that's good. So here I am at the call, and you can see here that we have, so it did what I told you here before. It actually pushed the address for the, basically the return address, which is the address right after the call, to the stack. There you go. So now what we are going to do is we are going to pop that address into SI and just re-show the registers real quick. SI is still zeros. Let's step into that. So now SI, yeah, it contains that 7C13 that we've seen, and then we just step into that. We subtract the hold on. Yeah, so we subtract 13, which is the I guess the offset of relocate from start. So now what we are going to do is we are going to initialize di with 0x500, and we are going to move 80 into cx. And here we are going to execute this instruction here that will basically copy the value in AX in DI all the way until CX gets to 0, right? And it copies as words. That's why we have 0x80. 0x80 is 128 decimal. Right, so let's step into that. Okay. And of course we need to step into that every single time, because here you can see that RDI gets incremented and CX which was 0x80, gets decremented. So now what we need to do is, let me just, what was it? 0700, and we want 100 bytes. Oh shit, too many bytes. Okay. That was not ideal. So what we want to do actually is, we want an address to stop at. We don't want the offset. There you go. Right. So here, if we go back, we are executing this. So we want our breakpoint here. So 7C22. So let's add a breakpoint 7C22 blist just to make sure. Yep, it's there. Right. So now we have finished executing the zeroing out of the stack region. So let's take a look at our registers. So here we've put 100 into CX. So basically 0x100 is 256. So SI is the correct address, 7C00. That's where we are copying from. And DI, where is DI? Yeah, DI is 0x600, which is the address we're writing to, right? So it's all correct. And now if we just take a look, XP, let's just display, and I'll display them from there. Actually, I just want 128. There we go. So here you can see that all the way to so between 500 and 600, we have all zeros, right? So that's great. Right, so now we are going to execute this instruction here, which is the rep nz move sw. And what we want to do is actually, I want to go and put a breakpoint at the jump so that we can let the copy do its magic. So the jump is at 7C to 4. So breakpoint 7C to 4. And let's continue. Oh, of course. I need to delete the breakpoint 2 because we still have a breakpoint at 7C to 22, which is the repenz instruction, right? So I need to delete 2, plist, make sure it's not there, and then continue. Right, great. And here we probably have an issue because it's trying to jump +0. Okay, I see. Right, so it's trying to do a near jump, which is a jump to a location given by an offset, whereas we wanted to jump into a location that's absolute, so an absolute address, not just an offset. So what we are going to do now is go to the code and actually specify the full address with the code segment. And actually, we could have just seen this if we looked at the assembly for this once it was generated. So that's something we will try to do. Objdump, if I remember. So Intel-M, this would be 8086. And we have just a flat binary file. So that's -b binary. And we want it to be deassembled, and we want a VMA adjust of 0x600 now, because that's where we'll be. And then the file itself is at build bootloader.bin. Okay, and we have an issue. Why is that? So unrecognized. Oh yeah, of course. It's sure. It's just VMA, not VMA adjust. Adjust VMA. M-A. Right. Great. Right, so we're looking at the jump. Great. So here you can see that it actually is taking the jump to a absolute address 0x29, which is at the 0x600 code that we've copied, which is great. So now we can just execute it and make sure that it's still working, and we'll be fine. Let me just put a breakpoint here, right at the jump. So I know it's 24, sorry, because that's the offset here to 600. So I'll put the breakpoint. Actually, let me just sort this first, and then just break 0x7c to 4. Right, and then continue. All right, cool. So here we are actually jumping at 0c, so 629. And what I will do also is I will try to disassemble the code at 0x600. And I know it's between 0x600 and between 0x800. So it's a full sector. So let's just deassemble that code and see what it gives. Right, so, and here we can see that we have very, very much the same instructions. And if we go to the address we're trying to jump to, so this is 29, this is 29. So here we can see that we are actually going to execute this next instruction here. And you can see that, for example, the boot drive variable is actually expected to be at 6c9 and not at 7c c9. And that's because we have moved that org directive to be 0x600, right? Great. So now that our first sector is done with, let's just keep running it. Okay, that's not good. So what we'll try to do now, what we'll try to do is let's try to debug the code that comes after this, because there might be something that we're missing. Right, so actually I think we didn't have any issue. It's just that we right, actually we are jumping into the second sector, but the second sector is actually just a random byte. That's why it hang. Okay, so there is no issue then, so let's just continue. Right, fine. Very well. Right, so this is it with the first sector. Well, if you have any notes or remarks, please let me know in the comments. If you have any questions also, let me know. If you want me to cover any other topic in detail, I'll try to do that. And yeah, I guess next time, I actually wanted to start working on the second stage now, but I guess that would be something we'll do next time. All right, until then, see ya, bye.